Hello. In today's Chapter 14, Lecture 7 video, we're going to be looking at Learning Objectives 3 and 4. So we're going to be looking at our rate of reaction using time and concentration, and we're going to look at rate of formation of product or disappearance of reactant using another substance if we have a balanced chemical equation. Okay, so our chemical reaction rate is based on the change in concentration of a reactant or a product over time. It's usually given in molarity over seconds. Okay, so if we take the reaction over to the right, we have A going to B. A and B are stoichiometrically equivalent to each other, so the rate of disappearance of A will be equivalent to the rate of appearance of B. So we'd say that the negative delta A over time would be equal to the delta B concentration over time because they are stoichiometrically coefficient. So if we look after 10 seconds, we would say that the change of A would be a negative 26 millimole per 10 seconds. That's not a true rate, but we would say that our delta A over T would be equal to negative 26 millimole over 10 seconds. And then if we look at that same interval between 0 and 10, our change in B over time would be equal to positive 26 millimole per 10 seconds. So because they are stoichiometrically equivalent, one is going to decrease at the same rate that the other one increases. We call this relating of each other a relative rate. So relating one rate based on the rate of another substance. So we can use these relative rate expressions to express the appearance or disappearance of any reactant or product. So relative rate equations can be used to express the rate of disappearance of a reactant or appearance of a product. So going from A to B, our rate is equal to negative delta A over T, or our rate could be equal to delta B. Okay. We call these a average rate. Over a given period of time. Because we're looking at our concentration at time A versus time B, or rather, our concentration at one point versus the concentration at another point, and we're doing the change in those concentration over the change in time. With our reactions, that rate changes constantly. So as a reaction proceeds, we're going to have fewer reactant collisions because there is a smaller reactant concentration, so our rate will actually go down. So in a reaction, the concentration of reactant particles is constantly going down. Which means we have fewer collisions, which leads to a lower or decreased rate. Okay, so our rate will actually go down over time. Okay, our rate goes down over time. So let's see if we can actually calculate a average rate for a substance. So let's look at chlorobutane. Chlorobutane reacts with water in the following equation. And we want to look at the rate of disappearance of that between 100 and 200 seconds. Okay, so we want to look at how chlorobutane changes over that time interval and determine the average rate. So our rate is going to be the disappearance of our chlorobutane over time. Okay. And again, this is our average rate. We'll look at other ways of describing rate, but right now let's look at average rate. So our rate is going to be equal to negative initial constant, this will be final minus initial. That's how you always do it. So our final concentration, so our concentration at 200 seconds minus our initial concentration at 100 seconds. So at 200 seconds, it looks like we have a concentration of around 0.068. And then our initial concentration looks like it's around 0.082. And these are both molar. And then we're going to divide it by our time range, 200 seconds minus 100 seconds. Okay. This gives us a rate equal to 1.4 times 10 to the negative 4 molar over seconds. Now, as a note, rates are going to be positive values, right? But our actual change in chlorobutane over time is going to be negative 1.4 times 10 to the negative 4 molar over seconds. We just use this negative here to cancel out the negative here to give us a positive value here. Okay. Let's look at what's called the instantaneous rate as well. So instead of using an average reaction rate, we can also look at what's called the instantaneous rate. And this is the rate at a given point. And this is almost always how rates are actually expressed, is as instantaneous rates. To calculate an instantaneous rate, you need a concentration of reactant versus time graph, as we have over here on the right. And we need to do a tangent line at a specific point. To calculate, I'm just going to do IR, instantaneous rate. So we need a concentration of reactant versus time graph. And we need to do a tangent line at the desired point. and then the instantaneous rate will be equal to the slope of that tangent line. And that slope of the tangent line, remember, is the change in y over the change in x. So let's try it for our instantaneous rate at 600 seconds. So here we have a tangent line that was formed at 600 seconds. And we're going to be looking at the change in x versus the change in y. So our slope, which is equal to our instantaneous rate, would be equal to the change in y, final minus initial. So our final is 0.018 minus our initial, 0.042, all divided by our change in time, final 800 seconds, initial 400 seconds. Calculate this out, small area on top, seconds on bottom, we get a value of negative 6.0 times 10 to the negative 5 molarity over seconds. And of course, that is going to be a change in chlorobutane. Our actual instantaneous rate would be a positive value. Okay? So, when we're looking at our average rate, we're looking at one product and reactant over a short period of time. And with our instantaneous rate, our initial concentration is what we're generally looking at. So with instantaneous rate, we want to look at the initial instantaneous rate. So with the average rate, it doesn't really matter where you start, but with instantaneous rate, you almost always want to look at your initial rate. So here, the concentration of reactant has not changed. So we're looking at what's going on right at the beginning of the reaction. With our looking at instantaneous rate, we're almost always looking to see how concentration is going to affect our reaction. So using that initial value where you have the highest concentration and not anything has really anything has really occurred is the best way to determine how concentration is going to affect reaction rate. So the way we do this, the way we look at how concentration affects reaction rate, is you vary one reactant concentration at a time. To see how its change in concentration affects rate. Okay? And then you can look at both or all three substances, depending on how many you have. You can look at all the reactants change in concentration, compare them to determine how to affect your rate using changes in concentration. And that's what we're going to do with a lot of our different rate calculations. Now, if we want to look at stoichiometry, we can also kind of accept the fact that, as you lose one substance, it should do it in such a way that is stoichiometrically equivalent, right? So if we have a reaction going from reactant to product, the rate at which you produce product should be the same rate at which you lose reactant. However, when we don't have one-to-one, like we saw with these initial reactions, we have to take into account stoichiometry. So stoichiometry kind of dictates the rate at which we lose or gain a substance. The disappearance of a reactant, or the appearance of a product relative to each other. So we're still talking relative reaction rates. So if we have AA plus BB going to CC plus DD, this reaction we need to take into account stoichiometry when we're relating the rate of appearance or disappearance of a substance. So we could give, for instance, if we look at the change of concentration of A versus time, we can use that information that we get here and relate it to any other substance within this equation using the following relation. So I'm going to use the stoichiometric coefficient within our relative rates. So if we have any one of these rates of our substances, we can determine how the other rates are going to be affected. So you can look at this and directly put it in for this portion right here. Remembering that the delta concentration over time is what we're actually talking about as a rate of appearance or disappearance of a substance. Okay? So whenever we have an equation, like we see here, we can go ahead, set this equal to A, C, C, D, D, and we can write our relative rates. So we would say that -1/2 delta N2O5 over time is equal to 1/4 delta NO2 over time, or 1/1, as we have no stoichiometric coefficient for O2, so we'll just go delta O2 over time. So if we have any one of these rates, we can relate them to any other rate. So let's just try over the interval between 0 and 1 hour, which is also equal to 0 seconds and 3600 seconds. So we're going to look at the way that N2O5 changes over the first hour of the reaction. So we start out at 1.4 molar, and then after an hour we are down to about 1.08 molar. So our actual change in N2O5 concentration is equal to our final concentration, minus our initial concentration divided by our final time minus our initial time. So our rate of disappearance of N2O5 is equal to negative 8.9 times 10 to the negative 5 molarity over seconds. And now this value can be placed into this portion of this equation, and we could solve for any of the rest of them. Okay? So we could say, okay, -1/2 change in N2O5 concentration over time is equal to, that's related to NO2, so, 1/4 change in NO2 over time, and we're going to solve for the change in NO2 over time by basically dividing by 2, multiplying by 4. And it's going to take, we're going to cancel out this negative because we're creating NO2. And what we get is the rate of production of NO2 is equal to 1.8 times 10 to the negative 4 molarity over seconds. Basically double, right? Because it's a 2:4 ratio between N2O5 to NO2, so we're going to create NO2 twice as fast as we deplete N2O5. So the rate is double. Okay, we can also relate NO2 concentration change and O2 concentration change. So we could do 1/4 times by 1.8 times 10 to the negative 4 molarity over seconds is equal to delta O2 over time. So it's basically, we're going to take that value we just got and divide by 4, and we get a change in O2 concentration over time equal to 4.4 times 10 to the negative 5 molar over seconds, which hopefully makes sense. We're going to produce O2 at 1/4 of the rate that we produce NO2 because there's 4 moles of NO2 produced for every 1 mole of O2. Okay? So we can relate all of our concentrations, all of our average concentrations. And that is everything for learning objectives 3 and 4. See you guys later.